Next we are looking at beta decay happening, and we first need to draw the beta particle symbol. So to do that, there are two ways to draw the beta particle symbol. A beta particle is simply an electron, so we can draw it. An electron has basically zero mass and a charge of -1, and we can put an E, or we can draw the symbol as with the beta symbol, so 0, -1, and then the beta symbol, which is kind of a funky looking B. So let's start. So lanthanum 141 is decaying, so we start by drawing our full isotope notation. 141 is of course the mass number, and then lanthanum, if we want to find that on the periodic table, it is actually just after, right here. Let's see. Right here. Oh, not on this periodic table. It's actually pulled down into the F block on this periodic table, number 57. And so we'll put in that number 57. I accidentally put a mark there. And then in beta decay, we are going to create that electron coming off. And then we need to make our numbers add back up to our original value. So I need to ask myself, what plus -1 gives me 57? So essentially, what minus 1 gives me 57? And of course the answer is 58. And then what plus 0 gives me 141? Well, it's still a mass of 141. Beta decay does not impact the mass of the isotope, but it does impact the atomic number because we have a neutron becoming a proton. So we increase our atomic number by 1, but since neutrons and protons have the same mass, we don't actually change our mass number. So all we need to do now is find element number 58, which is right here, Ce. And so we will fill in that chemical symbol. And we can just put our 0, -1, E, and then the shorthand for our isotope Ce-141. Next we have calcium 40 decaying. Whoops, didn't mean to draw those lines. Let's get rid of those. Calcium 40 decaying, Ca40. And then we just find calcium on the periodic table. It's right here in the S block. Calcium has an atomic number of 20, so we can fill that part in. And then it of course is decaying. One of the products is of course our beta particle. And then our other product is going to have the same mass number of 40, but is going to have an atomic number that's 1 higher than calcium. So an atomic number of 21, because of course that makes 21 plus -1 get us back to our original atomic number of 20. A neutron is becoming a proton, and so instead of calcium, now we have the element of scandium, Sc. So we'll fill in our answers, Sc-40, and then our beta particle, or our electron. Now we have strontium 90 decaying, so we'll start by drawing our full symbol, strontium 90, and then of course strontium's atomic number is number 38. It's right here on the periodic table, so we'll fill that part in. And we know in beta decay we're going to get our beta particle, and we will get an element with the same mass number as our original element, but an atomic number that's 1 higher. So now we are at element number 39, which is yttrium, capital Y. So we'll just fill in the blanks, yttrium-90, and our beta particle. Then we have Ra230. We'll start by writing our full isotope notation. 230 at the top, and we need to find this element on the periodic table. Ra is right here, number 88, so we can fill in that atomic number 88, and now it's undergoing beta decay, 0, -1, and this time I'll use the beta particle symbol, the beta, plus something with the same mass number, 230, but an atomic number that's one higher. So now it is at 89, which would be element AC. AC. Well, then we'll write our shorthand notation, AC-230. It's good to practice writing those different notations. And then, of course, the beta symbol, 0, -1, beta. Last but not least, we have uranium-238, which is decaying. We'll start with uranium-238, and then we'll go and find uranium's atomic number, which is 92. That may be one you kind of already have a sense of. You kind of know where it is in the periodic table. Uranium is decaying into a beta particle, 0, -1, and an element with the same mass number of 238, but an atomic number that is now one higher at 93. So that is Np. So we'll fill in Np238, and then our beta particle symbol, 0, -1, beta. Last but not least, we will look at gamma decay, but gamma decay is actually easier than all of the other types of decay we've done before, because gamma radiation is basically just energy, and so it doesn't actually impact the mass number or the atomic number of the element at hand. All that it impacts is it gives off a whole bunch of energy, and so in this case we don't actually need to write out the original isotope because we know we're going to end up with the same thing in the end. So let's first draw the gamma radiation symbol, which is the Greek letter gamma with just 0 at the top and 0 at the bottom, because it has no impact on the mass or the atomic number of the element. So for each of these decays, we'll go ahead and fill in that symbol. 0, 0, gamma, 0, 0, gamma. And then we will fill in the full isotope symbol for the element at the end. For extra practice, you could, it doesn't tell you specifically that you need to do full isotope notation, so you could just write uranium-235. That would be acceptable here, but I'm going to go ahead and write out the full isotope notation, uranium-235. And then find uranium's atomic number on the periodic table, which of course is 92. So I'll fill in that 92 at the bottom. AM-247, so we'll write that full isotope notation, AM with 247 at the top. And then, of course, it is number 95. If you come down and find it down here, number 95, so I'll fill in that atomic number at the bottom. And then last but not least, TH235. We'll write TH with 235 at the top, which is also an acceptable isotope notation. You don't necessarily need to put the atomic number every time, but then TH is number 90, so I'm going to go ahead and fill in that atomic number at the bottom as well. And that's really all there is to gamma decay. There's no impact on the atomic number or the mass number. All it is releasing is a whole bunch of energy, and that's what that gamma particle is representing.